Alright, I think that's got it. Alright, this is 211. We're going to do circular motion. We did projectile motion. That's a lot. Circular motion is a lot as well. I will tell you straight up, people tend to find this slightly difficult. Once you see the symmetry of it, maybe it won't be as much. But you got to think of it in terms of angle as opposed to think of it in terms of distance. So before we had distance and displacement, here we're going to have rotation and angle change. Rather than distance change or displacement change, angle change here with circular motion, okay? So one of the things with circular motion, you got to be able to see it, right? Here's a eye bolt I had laying around. Some Kevlar string. Now be careful not to hit my fluorescent light up above me, or I think the cat left. Alright, so circular motion goes like this. And circular motion, now I'm trying to keep it as uniform circular motion. What we're going to deal with, since it's uniform means the same, that means same at all times. And if that's true is, the velocity here, 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 and there, 90 degrees apart, should all be the same. But it goes in different directions, so really it's the magnitude of that velocity that's the same, not the actual. They call that tangential velocity, because that's the velocity tangent to that circle. So the velocity there and the velocity, I'm going to release at the bottom this time, close to the bottom. This has got dust on it. Look what I used to do. Oh, I managed a pumpkin chunker contest one year. Alright. So, let's think in terms of circular motion, rotation. You know, there's an old song, you spin me right round, baby, right round, like a record, baby, right round, right round. I won't start dancing. It would be sad. You can think of spinning around. You got to visualize this, though, guys, gals. You got to visualize it, okay? So let's start out, and this is section 4.4, uniform circular motion. We got out some radius r here. And out some radius r. At this point, you've got some velocity. At this point, some velocity. At this point, some velocity. And we'll just... So in this case, in the rotation is that way. So we're spinning around like this. Release it right here. It's going to go straight this way. Straight across and up at an angle there. Okay? So let me label this a little bit. Okay, that's good enough. I'll just say that these are, this is tangential velocity. You remember the word tangent from trig. Rise over the run, opposite over adjacent. Rise over run slope, my apologies. It's opposite over adjacent for a right triangle. Tangential can also mean just barely skimming it and hitting at one point. That's a tangent line, we call it. I'm not going to get into why they call it that. Alright. Now, for uniform circular motion, this velocity here, how do we find the magnitude of that velocity? Well, it would just be how far you went around over the period. So you could say for the whole circle, it's the circumference over the period, the time for one rotation. So in this case, we'll call that circumference is 2 pi times the radius, and capital T will stand for the period of one rotation. I'll write that in something a little better. Okay. Now, That's how we find the magnitude of that tangential velocity. Okay, let's look at, rather than this, let's blow it up just looking at one little bit on angle. We're going to need to do that. And so let's set up a coordinate system here. And my dogs are running around. Lily, what you doing? Lily, what are you doing? You want to show everybody? You want to come on camera? Come here. Come here, Lily. Come here, girl. Come here, Lily. Come here, Lily. I know, Misty. Come here, Lily. All right, this is my dog, Lily. Oh, I'm sorry, Misty. I stepped on your toes. This is Lily. Hi. She. Ooh. I know, Misty. You want to be on camera? Okay, I'll pick you up to no. You want to be on camera? Come here. Come here. Wow, you don't want to be on camera. Okay, I see you now. I got to go back to work, okay? I go back to work. All right, see you later. Missy doesn't like being picked up. She's a collie, and she just gets all frustrated about that and weird. Let's look at go out to some point here. This is going to be the radius out at that point. This is going to be, the book calls it a particle. It's just a point on a circular motion. Whatever's running around in circles, race car track, people, bugs. I don't know. You ever tied fishing line to legs on a grasshopper? I actually did that as a kid. It was kind of, the legs always end up getting pulled off. On the bigger ones, they don't as much. And you get them to fly around in circles a little bit. I never could do it to a fly. I guess you could lasso a fly and then get horsefly might work. But they bite. But I never did that to a fly. But if you could have a horsefly running around, that'd be kind of cool. Have a little pet horsefly running around. What is it that bites you? Regular fly would be better. But you can have a particle right here just running around in circles. So if you want to think of it, the way it's moving in this arc like this. That's the arc it's moving in. That's not the best circle. I'm sorry, but I think you get the gist of it. And so what we're going to do, we're going to call this S. We're going to call this angle here theta. Call that angle theta. And what we're going to say is we're going to find the angle theta. Theta is actually defined 3 lines. That's like super equals. It so super equals it, we're going to call it a definition. And that's kind of how they define it. Theta, by definition, is going to be the arc length over the radius. What is the arc length? That's S. It's not a straight line. That's a curve. That's a curve. S over R. All right. S over R. And that angle then, in this case, is measured in radians. This is where the term radians come from. It comes from the radius of that. All right? So theta, that angle that it's rotated, is defined as arc length over the radius. Okay? So for a full circle, S equals, what's all the way around for a full circle? Well, we know that's 2 pi r. So theta for a full circle, 2 pi r over r, that cancels, it's 2 pi. So why are there 2 pi radians in a full circle of angle? That's why. How we define theta. How we define an angle. Arc length over the radius. We use degrees because it's easy, and with, divide into 360 little, each circle in 360 little arcs. But that's the definition of it. We just use radians, and we converted radians. You convert from radians to degrees, of course. 2 pi radians would equal what? Of course, if you need to convert, 360 degrees. So that's your conversion factor. Okay. Some people use pi over 180. Why memorize that stuff? Just know all the way around. 2 pi over 80 and 360 degrees sets you up a ratio. As long as it cancels, factor label method from chemistry, it works. Okay? You learn as little as possible. All right. We would also, the book says this is also 1 revolution. So we'll say that's 1 revolution. They go in to find how much 1 radian is. That's not worth it. A lot of times, though, you'll see this written as arc length equals r theta. And this, remember, let me see if I can get that better. That's not much better, but you get the idea. Arc length equals r theta. However much travels in arc, that distance in arc. Now, to make this valid, though, theta must be in radians. So if you want to know how far you travel along the edge of a circle, as long as you know the radius and the angle in radians, you can find how far you travel along that circular path. Okay? So this is kind of like position and displacement a little bit. Then we went into velocity. So here with angle, we don't have velocity, just straight line. We've got how much the angle changes. So we're going to talk about angular velocity. Okay? It's how fast the theta changes. Or angle changes. You could call this rotational velocity. How fast it rotates. So many RPMs. That's in revolutions per minute. Angular velocity, just like regular velocity, has units of angle over time. So what would those units be? Radians per second, degrees per second. That makes sense. Now they go through a little derivation. I'm not going to go into that. I'm trying to make the connection between linear and angular. So if this makes rather meters per second or feet per second, the equation for regular linear velocity was distance over time, or displacement over time. I'm sorry, distance over time would be speed. For angular velocity, we're going to use omega. Greek letter omega. It's not a W. It's got little humps at the bottom of it. Omega there. Omega is going to be d theta dt. That's in differential mode. You can also write it as in terms of deltas, delta theta over delta t. Change in angle over change in time. How much the angle changes in a certain amount of time. You're doing curls. You know, if you think about it, your arm is doing, you can get a rotation of it, a rotation rate, a rotational velocity of that arm. Because it's an angular motion there if we keep that elbow fixed like you're supposed to. Okay. Graphically, just like velocity is the slope of a distance versus time graph, omega is the slope of an angle versus time graph. And we could do as before with velocity, we say final position equals initial position plus velocity times the time. That was one of their equations. You could derive an angular version of this exactly the same. It's just, it's same play, different actors. Okay? But as opposed to final position equals initial position, it's rather position, we're doing angle, and I'm going to put this down here because I'm running out of room. We say that final angle equals initial angle plus the angular velocity times the change in time. Angular. So this is an equation just like we had for linear motion. Same for angular motion. And we could graph this out. And then they do graphs. Example 410 does graphs on this of it. All right. Now, use an angular velocity and the period, because what you can say is, let me see where I'm going to put this. I'm going to put this up here. Okay. I'm going to stick this up here. What you can say for one period, the angular velocity would be, for one rotation, I should say. I'm going to say for one rotation. The angular velocity would be how far it went around that distance, 2 pi angle, because we said one full circle was 2 pi radians over the period. 2 pi radians over the period. Let me put this in radians here. So that's another way, if you know the period that something's rotating, you can find its angular velocity. That's a little different, but that's okay. That's just the way it because it rotates back on itself. You can do this sort of thing. Straight line doesn't come back upon itself, so you can. Now the question you may ask is, well then how do we relate this to this? Well, wait a minute. This tangential velocity here, this tangential velocity, that's equal to, but the magnitude of that tangential velocity, 2 pi over the period times r. Now, that's a t there. Now, I put that in parentheses on purpose. Aha. Can we substitute in omega for that? Omega being the angular velocity. Well, yes, we can. We can then say that the magnitude of the velocity, that tangential velocity, how fast the speedometer on your car would say as you're running around that, well, this way around that circuit, it would just be your angular velocity times your radius. Your angular velocity times your radius. Okay? And those are the basic equations for angular motion. Now, without accelerating. This is not taking into account acceleration. That's in a different lecture. So, this one. Yeah, you can know that one here and here. And if you do that, that works out. Okay? There's some problems with it. You just kind of work them. They're very similar to others. I may do an example problem on a lecture, or I may put some stuff on Canvas of people doing that. Uploading, because it's so slow here. The barn cat did show up, so we got to show the barn cat. Miss Chloe. Say hello, Miss Chloe. Can you say hello? Say hello to the camera. Okay. She kind of stays out in the barn a lot, and she comes in the wintertime because she don't like the cold. Okay, there you go, girl. Okay, so we'll do acceleration on the next one, but that's section 4.4.